Hello everyone. This particular video just goes through practice problems for chapter 6. So a good way to prepare for the test. So finding the area of the shaded region. Here's my shaded region. We'll go ahead and put that in blue. This is what we're trying to answer. What is the area there? Now if I use my table, remember that my table only gives me the area under the curve from the end to the z-score. That's what my table is going to give me. And let's pull up that table. It is a positive z-score of 0.59. So at my table, I'm going to come here 0.5 and then come all the way across. And 0.59 would be 0.7224. 0.7224. So remembering that it's here, and the table says 0.7224 is the area. But I don't want the area that it's shaded yellow. I want the area here that's shaded blue. To find that area, because the entire area under the curve is 1, I'll say 1 minus 7.7224. And of course, when we do that, we get 0.2776. The other way, of course, that we can find the area under the curve is to use our technology. So with our calculator, I'm just going to move it over here so we can look at our picture. I'm going to use my distribution. So second distribution, I'm going to come down to normal curve. I'm going to choose number 2. And once I get here, now remember, this is my operating system. Those of you who have a earlier operating system, it'll just say normal CDF with a parenthesis, and you're going to put in the numbers that I'm going to put in, but you're going to separate yours with a comma. Mine just kind of steps me through it. So my lowest n, meaning my smallest z, here is 0.59, and it goes all the way up to the end of the curve. So I don't have to subtract 1 or anything. I can just put it in as is. So I'm going to enter 0.59 as my lower. My upper is all the way to the end of the curve. So to make that happen, I'm just going to put in 99999. I'm going to leave my mean or mu at 0 because this is a standard normal curve with my mean of 0 and my standard deviation of 1. And then I'm going to cursor down to put paste. Remember those with the other would be having a parenthesis, 0.59, comma, 99999, comma, 0, comma, 1. You're going to close your parenthesis. I'm going to hit enter to paste, and I'll have the exact same thing that you have on your screen. Once that's there, we press enter, and we find that the area is 0.27759, which of course would round to 2776. So looking at the next one, I want to find the area of the curve between negative 1.82 and to the end of the curve. So let's, a couple ways that we can do that. I want this area that's shaded here in yellow. That's what I'm looking for. When I go to my table, again, I'm just going to get this area if I were to pull up a negative z-score. So we could do the negative z-score and find this little area, no problem. I can also, though, use my calculator again. I'm going to go again, second distribution. We're going to cursor down to normal curve. We're going to say my lower limit now, all the way at the end, is negative 99999. we're going to cursor down, and the upper is negative 1.82. I can do that. And if it does that, I'm going to get this area down here. Then I could subtract it from 1. To get the yellow area, I would begin at negative 1.82 and go all the way up to the farthest we could go. So let's bring that calculator back up. But it's important you understand these concepts. So negative 1.82, cursor down. I'm going to fill that in with 9s. And again, I'm going to leave mu at 0 and standard deviation of 1 and paste. And now you've entered it with your commas. We should be all ready to find out. And we find that the area is 0.9656. Finding this area in number 3, we're going to use the same method. We're going to get that calculator. You can see we're going to use the calculator a whole lot today. I want between negative 1.08 and positive 1.08. So again, I'm just going to go to my calculator, put in my negative 1.08 as my lower end, my upper end being positive 1.08. Again, I'm going to leave mu at 0, standard deviation at 1, and paste, hit enter, and I find that area is 7.199 if I round that last amount. Let's continue here with 4. Now 4 flips things on you. Now we're finding z-scores. We're not finding area. We are given the area. So we know that this area is 0.4013. It's very important you don't confuse z-scores and area. Critical. Remember, your z-scores are the numbers here along our horizontal axis, like a number line. My area or the shaded area, like you would find the area of a square or find the area of a rectangle. It just so happens that the area we're finding is the area that's underneath that curve. So again, I have to think about this because I'm wanting a z-score, and I know if this is 0, and I'm on a number line, going this way is going to be positive numbers. Going this way are going to be negative numbers. Well, because this z is here, I know that this is going to be a negative z. It's got to be. So I'm going to go to my table first to show you how to do it at your table. We're looking at a negative z. And when I'm looking at negative z, I'm now remembering that in my table, I'm looking for the area of 0.4013. 0.4013. So I'm going to hunt down my table here and find 0.4013 is right here. 0.4013. And I'm going to be able to find that my z then would be negative 0.2. And if I go all the way up on this column, 5. So it would be negative 0.25. Let's pull up our calculator and show you how you can do this on your calculator as well. So I'm going to do second distribution again. Well, this time I'm looking for the z-score. I'm given the area. So I'm going to cursor down to number 3, inverse of the normal curve. Here I'm going to put my area, 0.4013. 0.013. And I know that mu is 0 and standard deviation is 1 because it's still normal standard distribution. So I'm going to press my enter. Those of you with the other operating system, you'll see right there that you're going to still come up with that button. It's going to have that open parenthesis. You're going to type in 0.4013, comma, 0 for your mu, comma, 1, and close your parenthesis and hit enter. And I'm going to find the exact same answer that I got when I use the table. Of course, z-scores must be rounded to 2 decimal places, and when I round this, it would be z. Whoops. Z will equals negative 0.25. These are 2 decimal points. Let's continue on with the next problem I have for you. Now the shaded area is 0.0694. So here is our area. So it's the bigger end. So I know that I'm going to want this z, and I know that z is going to be a positive z. If I were going to use my table, I would have to take 1 minus 0.0694, find out what this area is here. Then I could find out that z. On my calculator, it's a little bit easier again. Again, we're going to use the second distribution. Cursor down to inverse. My area now is 0.694. So I would have, if I'm entering this area, it would be the same if I can use it by reflection. If I said this area, those 2 areas are equal because of symmetry of the curve. So I can enter this into my calculator, and it will just remind me that it's going to come up with a negative, but if I flip it, it's still going to be then a positive. So we're going to put point 0.694, cursor down, and hit enter, and enter, and it's going to tell me it's negative 1.48. Negative 1.48. So this z will be positive 1.48. So let's see how we could put that in our calculator so we don't have to remember the positive negative. So we can say second distribution, cursor down to inverse, and we're going to take 1 minus 0.0694, and that area would then be 0.9306, and again leaving mu at 0 and standard deviation of 1 and 0 amperes. And guess what? I'm going to get the same area, but this time it's negative or positive, and I do want the positive. I'll pull over that screen for you. So the same thing is going to occur with the next problem. I wanted the shaded region, but remember on this side now, it's again the opposite. Remembering though that my z, right where it is now, my z will be a negative z. So I'm going to do second distribution, cursor down to inverse normal, because again, I have my area and I want my z. So now I can take 1 minus 0.8599, I'm not sure if I think maybe even the calculator will do it for you. 1 minus, let's try it, 0.8599, and leaving mu and standard deviation there. And they gave me negative 0.1079, which is the correct answer. So you can put your math right in there and it does it for you. It's too darn convenient with this calculator. I'm going to round to 2 decimals, so it's going to be negative 1.08. So here we go, and we're probably going to have to get some more space. Let's see how we do. The probability, using the standard normal variable, find the probability that z lies between 0 and 3.01. So my suggestion is every time you have a problem, you just sketch it out. Take the time to sketch it out. That way you will not be confused. So if I draw my curve, I've got my mu at 0 and 3.01 is going to be way here at the end, and I'm going to take the time to shade the area that it means. That helps me keep z-scores and area from being confused. So I'm looking from 0 to 3.01 and I'm looking for area. So on my calculator, I'm going to go to second, distribution, and now I'm going to use normal curve. So my lower is 0, my upper is going to be 3.01, and I'm going to enter and come down here to paste, enter, and enter, and I'm going to find that it's 0.49869, but 4987. So 0.4987. Again, here's the probability that z lies between negative 241 and 0. So we'll just sneak this little curve in here. There's 0. And here's negative 2.41 again because I've drawn my picture. I'm looking for probability, which means I'm looking for area. And when I have to shade, that is another telltale sign that that's what I'm looking for is my area. Again, second, distribution, cursoring down to normal. I'm going to put my lower now, and we always have to put lower to upper going from left to right the way we read, and of course that's going to be negative 2.41, and going up to the upper it would be at 0. Cursoring down, hit paste, and of course I find that area to be 0.4920. 0.4920. And again, I'll go ahead and pull that over for you. So these other ones are going to be exactly the same. You're just going to put the lower, the upper, the lower, the upper. It's the same process. Here, again, make sure you sketch the curve. So we'll go ahead and do this one as well. The probability that z is greater than 0.59. So here's 0, and of course I have a positive, so my positive is going to be here, 0.59. I want the probability, there's that P out there, so I'm really going to shade this So I'm looking again for area, and we'll find that by doing second distribution, cursoring down to the normal curve. We're going to have the lower limit now as being 0.59, and my upper limit, it goes all the way to the very, very end of that curve. So 9999, 0, 1, it's still yep, they're still in the normal distribution. And enter, and it's 0.2776. So 0.2776. Now we're going to move to a problem that is a non-standard, meaning my mu is not 0 and my standard deviation is not 1. This is find the area of the shaded region, but this graph depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. So two different ways that we can do this problem. The first is we can convert our non-standard scores to standard z-scores, and to do that we use the formula that says z is equal to x minus mu divided by the standard deviation. In this case, we realize that the mean is 100 and the standard deviation is 15. Well, I want the z-score for 110. So I'm going to write 110, that's my x, minus mu, we know that mu is 100, and we're going to divide that by the standard deviation of 15. And we do that math and we find that z is 0.67. 0.67 is my z. Again, I could go to my table and find the area under the curve to z at being 0.67, and I can do that because now I have standardized my scores. I have put them in the standard z-score equivalent. I can also go to my calculator and do second distribution, remembering that I have the z-score, so I'm looking for area. My lower is going to be negative 99999 because it's the end of the low end of the curve. My upper is going to be 0.67. And because I've standardized it and put my z-score in there, I'm going to leave mu at 0 and the standard deviation at 1. And we will find that that's going to be 0.7486. 0.7486. And I can stick that down there for you. Now, the other thing that we can do is let the calculator work for us. We can put in those numbers. So second distribution, I'm still going to go to the normal curve, but I can tell it what I want mu to be and standard deviation to be, and it calculates the z-scores and puts everything standard as I need. So my lower limit is going to be 0.999. But my upper limit, I'm going to put my actual score in there. I'm going to put 110 because that's what I want. Mu, I can enter as 100, and the standard deviation I'm going to enter as 15. So I've given the calculator everything about this problem. All I have to do is go in, and again, those of you with a different screen would be putting the commas between these values and hit enter, and guess what? I get the exact, or darn close to the exact same answer, 0.7475. I know that there's going to be some variation depending upon how you do this. It's just with rounding. I completely understand, because if I did this calculation for our z, I rounded z and it would have been 0.66666. It's a repeating decimal. Well, because of the rounding, that's why it comes up to be a little bit different. So I expect that little bit of difference, and of course, on your test, I will be checking your answers to see that if it was just that much off, and that's why it's off. So here's another one about our IQ scores. Again, mean of 100, standard deviation of 15. I want to know the area of the shaded region. That's when my IQ score is 85 and 125, and I want to know between them. So again, I can do that by going second distribution. My lower end this time is 85. My upper end is 125. My mu is 100, standard deviation is 15. I'm going to go ahead and enter, and I find that to be 0.935, so 0.936, 0.7936. So what that means is if we picked one person out of the population, it's a 79.36% chance that that person would have an IQ between 85 and 125. So that's the majority of the population, obviously. So these are very similar to the one we just did. Again, I'll just gonna do one of these, and I'm gonna suggest that you draw a table or picture every single time, because that will help you keep track of what you're inputting into the calculator and what you're trying to find. So let's do 16. The mean is mu is equal to 15.2 with the standard deviation. Sigma is equal to 0.9. Find the probability that X is between 14.3 and 16.1. So my mu is 15.2. I want to know that X is between 14.3 and 16.1. Well, obviously 14.3 would be here, and 16.1 is going to be somewhere up in there. So I want to know between. Since I want to know between, this is what I'm looking for. And again, because I'm shading, that's the other thing that reminds me that I'm looking for the area. I'm looking for the probability. On our calculator, again, we're going to do second distribution, cursoring down. My lower end is going to be 14.3. My upper end is going to be 16.1. Mu is 15.2, and if you'll remember, my standard deviation is 0.9. So you put all of that information in, and you'll find that answer is that 0.6827. So 0.6827. And this one is number 16. So let's keep on going here. And again, problems 17, 18, and 19 are very, very similar. So let's do problem 17. I'm going to draw my sketch of that picture. So I have a normal curve. Sorry, that's not a straight line there. It has a mean of 0.3 inches. And it has a standard deviation of 0.01 inches. The percentage of bolts, I want to have a diameter greater than 0.32 inches. 0.32 inches is bigger than 0.30 inches. So I know it's going to be somewhere here, 0.32. Because this is mu, that's the same as saying mu is at 0. So I know that I'm at my big end here. Let's go ahead and I want greater than, greater. So the area that I want is here. Once I have my picture drawn, it's very easy then to enter the numbers into the calculator. Second distribution. Again, my lower end now is going to be 0.32. And I know my upper end is 999,999, and my mean is 0.3, and my standard deviation is 0.01. And enter, and I'm going to find that that is 0.0227 or 0.0228. And if I want to write that as a percent, I'm going to say 2.28%. Number 20 is just knowing the rules of what is a biased and unbiased estimator from samples that are taken, and whether or not the sample median is a good estimate, and the answer is no. It is not. And number 21, it requires a little bit of work, but when we go through number 21, you will see that the median will not be a good predictor of the population. Because if I'm going to consider this, we have a pilot project. The numbers of people in the household are 2, 4, and 10. So I'm going to consider the values of 2, 4, and 10 to be my population. So considering that, and if I had the population median, the population median, and if I go 2, 4, and 10, the middle number is 4. So my population median is in fact 4. Easy to find, easy to see. But I want to know if that taking a sample from that population, if that median is a good predictor for my population median. So here are the different samples that we could get when we take an N of 2. This is a whole list of them here. So let's make a table. It won't let me do enough tables, so we'll get that. Um, Makes it very big too. So let's just instead do the table by hand. That'll be a little easier to see. It won't let me delete that. I don't want to delete the whole page. Okay, so instead, we'll just go ahead and make a quick table by hand. We'll list the median of each sample. So it's sample medians is really what it is. So, and we'll go ahead and keep a frequency. Because it'll just help us total it a little bit. Okay, so my sample mean, my first sample is 2, comma 2. So I have a sample of 2 and 2 are my sample. So of course the median is simply going to be 2. I have the next sample of 2, 4. The middle number, the median, the one in the center is going to be 3. Here I have 2 and 10. Of course, the middle number there, I'm going to add the 2. 12 divided by 2 is 6. My next sample here is 4 and 2. Well, between 4 and 2, again, I'm going to add 4 and 2 and get 6 divided by 3. So I have another sample median at 3. So here's my first one. Should have done that as we went. And here's my second one, that's 3. Here we're going to have 4, 4. So of course my median is simply 4. We have one of those so far. 4 and 10. If I add 4 and 10, I get 14. Divide by 2, I get 7. And of course I have one of those so far. My next one is 10, 2. Adding those and dividing by 2, I get 6 again. So I have another 6. 10, 4. Adding those again. 14 divided by 2 is 7. I'll have 2 of those. And lastly, my last sample is 10, 10, which of course gives me 10 as a sample median, and there's one of those. So here's my frequencies. Well, how many different ones do I have? There are 9 different samples. So each of those had 1/9 of a possibility. So now we're going to put probability here. So since each sample had a probability of 1/9, when there's 1, it's going to be 1/9. However, if there's 2 ways that I can get a median of 3, I'm going to put 2/9. 6 is going to be 2/9. 4 is going to be 1/9. 7 is going to be 2/9, and 10, of course, will be 1/9. So once we've gotten our chart ready and we've gotten everything done, we can go to our calculator and we're going to input this data into our lists. We've done that before, so let's go to list. We're going to edit our list. So in L1, I'm going to put my medians from each sample. So we have 2, we have 3, we have 6, 4, 7, and 10. In L2, I'm going to put their frequencies or their probabilities. I'm going to go ahead and put their probabilities. So in L for 2, my probability is 1 divided by 9. And it's going to do the math for you. And then my 3, there were 2 3s, so that's 2/9. 6, there were 2, so that's 2/9 again. 4, there was only 1, so 1/9. 7, there were 2 samples. We had a median of 7, so that's 2/9. And lastly, there was only 1 sample had a median of 10, so that's 1/9 as well. Once I have my data in, I'm going to quit. I'm going to, how about if we just clear the screen here and make it less messy? Let's go back to stat. Let's go to calculate this time, and I want the one variable stats. And again, my frequency list is L1. Those of you with the other operating system, as a reminder, once you get one variable stats, you have just a blank, it's all it says. You're going to type in L1 by hitting second, L1, then you're going to hit comma. To get my frequency list, I'm going to do second and 2, which is L2. And everybody's going to put L2, and then you're going to have a parenthesis. I'm going to press calculate, and it's going to give me my stats. Well, I went ahead and got it before I read, but I knew I was going to need them because once I did this, find the median of the 9, we summarized, we did that. We want to compare the population median to the mean of the sample medians. So we want the mean of the sample medians. Well, my lists are my medians, and we can just pull this up and say what I'm looking for then is my mean, my mean here is right here. Well, my mean of the sample medians is 5.3. So my sample medians, and it's the mean of the sample medians, is equal to 5.3. My population median is 4. You can see that the median is not a good estimator of the population. Okay, here we have several different application problems. We're going to do those again on our calculator. Again, my recommendation is you always draw the picture first. This is where we're going to move now into using the central limit theorem, because I'm not picking one annual snowfall as in the first one. I'm going to be picking 25 random years. So 25 random years. So because I'm picking 25, I'm picking more than one. I have to use the central limit theorem, which says that I'm going to change my standard deviation for my calculations. What's nice is that mu, the sample of the samples, is equal to the population mu. However, the standard deviation of the samples is equal to the standard deviation divided by the square root of n, and the square root of n here would be the number of the ones I'm taking. Well, you have to remember that there's qualifications on this. Either we have an n greater of 30, which in this case we do not, or the original population is normally distributed. So because it is normally distributed, we can use the central limit theorem. And you're not going to have one that you can't, simply because that would require a different calculation, and that's called bootstrapping. So here we're going to find our new standard deviation, and that's going to be equal to the standard deviation. Well, the standard deviation was 10. We're going to divide that by the square root of n, and n is 25. Sorry, looks pretty scrunched in there. And really, what do I have? 10 divided by 5, which is 2. So my standard deviation of my samples is 2, and I'm going to use that now in my calculation to find out the probability of the mean amount of snowfall during 25 randomly picked years will exceed 72.8 inches. So just like we've done with our other ones, we're going to go into second, well, I'll clear everything out again. Second distribution, it's a normal curve. My lower end, and we didn't draw that picture, let's go back because I want you to be in the habit of drawing that picture. My mean, well, that was a bad looking mean. Huh. Is 70 inches. And I want to know the probability of 25 of them will exceed 72.8. Obviously, 72.8 would be here. And I want to know greater than, exceed is a greater than. So when I do my highlighted, it's just going to be this area here of the tail. So we're going to bring over our calculator, and my lower amount is going to be 72.8. See how that makes it so it's completely unmistakable of what you need to put in. My upper, of course, I'm going to go to the very end, so I am going to have 9999. My mu is 70. Here's where you need to be careful. It says that the standard deviation is 10, but that's if I'm only picking one. But I'm not. I'm randomly picking 25, and we had to do this calculation to find out what my standard deviation of the samples would be, and it's going to be 2. So I'm going to use 2, and I'm going to cursor down and put paste, and I'm going to find out that it's 0.08075, which is 0.0808. If it asks you for the percent, 8.08%. So all of these are similar. I'm going to make sure that every time I do it, there are more than one selected. Here, there's 9 selected, so I'm going to use the same formula. Next, we are doing 50 different, so again, central limit theorem. And here, if 40 mechanics are randomly selected, again, 40, it's greater than 30, all these are greater than 30. I'm going to go ahead and use my central limit theorem, get my new standard deviation, and go through the problem. Same here, I'm still at 40. Here, I only have 24, which is not greater than 30, but that the mean of this test scores is greater than 78. And we're going to use that it was normally distributed at that point, okay? Now, I will caution you that once in a while you will get a slightly different answer, and again, that has to do with the variation of when we round, because sometimes we round, sometimes we don't round, and that is where you're going to get that little bit of variation, especially if you're punching the numbers into the calculator and putting the actual values in from mu and standard deviation, rather than standardizing them to get to a z and then leaving it at 0 and 1. So all those are all the same. Number 28 and 29 are very, very similar as well. We want to find out, and this goes back to the central limit theorem, it says that the population of 210 women, the heights of women are normally distributed, has a mean of 64.4 inches and a standard deviation of 2.9 inches. If 36 women are randomly selected, find the mean of the samples and the standard deviation of the samples of the population of sample means. Assume that the sampling is done without replacement and use a finite population correlation factor. So here we go. The nice thing is the mean of the sample we say is the mean of the population, which of course would be 64.4 inches. We also know that the standard deviation of the samples would be the standard deviation divided by the square root of n, which of course would be 2.9, and I am then going to divide by the square root of 36, which is really 2.9 divided by 30, or divided by 6. So 2.9 divided by 6, and I'm going to get 0.48. And here's the thing. Here's this rounding thing, and we know if we're rounding correctly, it's going to be 0.48. Now I know on your answer key it says 0.44, that there was an error on the answer key. The answer is 0.48. The next one is very similar. We're just going to do the exact same thing we just did, and very similar to the ones above. I hope this video helps you as you go through those practice problems as you prepare and study for the test.